Hello, everyone. I'm Elvira Rakova, and today on our AirG podcast, we have Paul Refalo from sunny Malta. Paul, it's really my pleasure to have you here. How are you today?
Same here. It's my pleasure to be on your podcast, on your interview, and I'm looking forward to have a discussion with you.
Yes, so Paul, I'm so happy actually to know that also in the sunny countries more south from Italy, there is a lot of going on compressed air. I was so happy to meet you last year, and today I would like to talk about the projects that are happening there. So Paul is the associate professor in the University of Malta in the Faculty of Engineering. Can you just tell us a little bit about your background and how you ended up to work with compressed air and pneumatics application?
Okay, good question. So as you said, yes, I'm an associate professor at the Department of Industrial and Manufacturing Engineering within the University of Malta. For those of you who don't know where Malta is a very tiny island of 300 square kilometers south of Italy, with 500,000 people as a population. So we're a small island, a small country. With one main university, it's the State University, the University of Malta. As I said, I am an academic within this department, and my research interests includes sustainable manufacturing, sustainable engineering within the manufacturing industry, and resource efficiency. And so this is where my interest in the energy consumption in manufacturing came from. And as you well know, this is why I'm doing also research in compressed air systems, because compressed air systems, unfortunately, do have a high energy tag behind them. They are energy intensive. So combining the ambition towards sustainability with energy intensive processes obviously became a logic step to combine them, and that is where my interest came from.
I always like to hear from people stories where how they actually ended up in compressed air, and everyone smiles and tell, "Ah, this is the interesting story. I started there, and this is how I ended up there." And a special pleasure I have actually to talk with academics, so people that go into the details and from the research side on this aspect that sometimes in industry is overseen, and people think just okay, it's compressed air, so you just do little fix here, you change the compressor and things will work fine. And when people think about making compressed air system better, the first thing is fix the leaks. So, and we have a very traditional auditors usually that come with the sensors, and a lot of our listeners know about it. So ultrasonic sensors, so they find the hole, and then they fix the hole or change the regulator. Could you please tell me about your project of the leaks? So what is this focus on, and when did you start it?
Okay, good question, and there's quite a story also behind that as well. So as you know, leaks are, let's call them the low-hanging fruits. The low-hanging fruits with energy-saving initiatives in industry, particularly in compressed air systems. However, even though sometimes, or many of the times, leaks are the obvious solution to do, so just go and fix the leaks. Unfortunately, industry sometimes just lives with these leaks. They just accept them and they live with them. And if they're bothering them too much, then they would fix them when they have their regular maintenance. If it's their monthly maintenance, or if it's a shutdown period for Christmas or for summer, when you would have, as you said, an auditor going around, or someone from the technical personnel, from the maintenance personnel, going around and fixing and hearing where these leaks are and fixing them. So what we are doing now, what our project is all about, we are trying to fix these energy efficiency sources, or inefficiency sources actually. They include leaks, but you could also have pressure drops and other faults, which we know that they do result in increasing the energy efficiency. So what we are trying to achieve is trying to have a system which can detect the leaks in real time. So rather than having someone going around the factory, the industrial system, with ultrasonic leak detectors, with microphones, or even with cameras, which could show you where the hotspots are, where the leaks are, we are trying to develop a system which could measure the right pneumatic parameters, monitor the correct parameters, which could tell us where the leaks and how big they are. So you might say, isn't this obvious? Just plug in a flow meter, a flow rate sensor, measure the flow rate. If it's higher than what it used to be, then there is a leak. Unfortunately, it is not that obvious. So it becomes a story of accuracy, whether you would believe the values that you have, whether you could detect even small leaks. And as we know, even the smallest of leaks could consume or waste a lot of compressed air, and compressed air at a high pressure comes at a lot of energy, using a lot of energy to generate. So even when these small little leaks, sometimes they go unnoticed. And this is what we're working on, coming up with a leak detection system which could monitor pneumatic systems in real time. We're trying to find out which parameters, and we're still working on this, which are the right parameters which can detect the size, the location, and the type of fault. So we would be able to say, okay, on that line, you should have a leak of approximately that size. So the technical personnel wouldn't waste time looking for these leaks, because a flow rate sensor, that is what a flow rate sensor would just tell you that you have a higher consumption. But the metrics that we are trying to develop would show you where and what type of leak you should find in a particular zone, in a particular region. We are trying also to develop a system which could prioritize the leaks. So if you had to go to industry today and ask them, do you have leaks? They would tell you yes. And we are aware that there are leaks, but we just live with them. We just increase the pressure. We just go to the compressor, increase the supply pressure, and we'll just live with that. But if you had to provide technical personnel with a list of leaks, and you tell them, listen, you can go and focus on these 10 leaks, because these 10 leaks are the main culprits. Now, from a factory, you only have 10 leaks which you can focus on. And maintenance personnel would find it much easier now to just focus on the major 10 leaks, rather than telling them that you have leaks all over the place. So that is another aspect which we eventually would like to develop.
I think it's really fascinating. So basically, you're not only developing the system that, as you said, just install the flow meter and see that the consumption is higher. This is actually one of the problems that I usually face. And people install fancy dashboards with all the flow meters, but there is no decision making behind this. So what I noticed that you localize it, you identify type of this, so the personnel knows what to do with this, and then you prioritize it. So you actually see it, what are the steps, what is the main cause here, and then it helps to identify all types of leaks that you have in the system. Do you focus on what type of the components you focus mostly on? So you mentioned pneumatics, so I guess it's cylinders, valves, filters, pressure regulators, all other components. Is it everything after the compressed air room for various types of industrial application, or it's more automotive or process automation? What type of the industry you see the application for a system?
We're currently focusing on the automation aspect. So automation used in various industries. We have plastic manufacturing. We also have an automotive case study which we are working on. However, the idea that we're developing, the solution that we are developing, wouldn't be so industry specific. So the way that we are developing our solution, it wouldn't make much of a difference when it comes to specific industries. So what we are working on are trying to identify the different pneumatic parameters which could be used to characterize different leaks. different faults. So whether it's a cylinder, whether it's a suction cup, whether it's a gripper, obviously the size of the leak would make a difference. So if you have a suction cup which is constantly wasting compressed air, because that's how a suction cup unfortunately works, is one thing. But then if you've got a horizontal or a vertical cylinder which is very intermittent, it just opens and closes, retracts and extends depending on its function, the function that it's carrying out, then it's another thing. However, the metrics, the pneumatic parameters which we are monitoring wouldn't be very actuator or end effector specific. Something which I wanted to also mention is that rather than just telling the technical personnel that you've got a leak in one zone, we are using machine learning and artificial intelligence to also monitor these values, these numbers, this big data. So we classify then the leaks using algorithms. So we try to classify these different faults and leaks in different classifiers, using different classifiers. Rather than just telling them that there is a leak, we're also trying to come up with a control solution. Ideally, the best solution would be to just go and fix the leak. Now, this is already a big step when it comes to reducing and mitigating these leaks. So an operator would love to know where the main culprit is, and they would just go there and fix it. But many of the times, they wouldn't have the time to run around and fix all the leaks. So we prioritize. If they can, they solve them. But we're also coming up with mitigating solutions. So how to live temporarily with leaks. So if you do have a leak which is reducing your pressure by so much, or if you have a leak which is not reducing the pressure much, but it's consuming a lot of air, how can I live with that temporarily until I solve it, until I fix it, but without reducing my productivity? In manufacturing, in industry, as you well know, if it works, we're fine, we can proceed, we can just go on. If it ain't broken, don't fix it, you know? So there's a leak, increase the pressure, and my machine is still producing as much as it should. So without reducing this productivity, we're trying to come up with control strategies. So you could reduce the pressure on one line and increase it on another. So decrease the pressure slightly where you've got a leak and increase it on another line to make up for it, to make up for the lost productivity. And these are the trade-offs which we are also studying, whether there are any control strategies based on the leaks which we would have detected and monitored to find the right solution which would decrease the air consumption, the energy consumption, but not the productivity, the rate at which the machine works.
This is really amazing. I think when people think about the leaks, they think that it's something simple, you know, and when people talk especially leak plus machine learning, they say, like, especially in our industry, in compressed air industry, it's a little bit old-fashioned, no offense to our listeners, but I mean, you say machine learning, artificial intelligence, and the leaks, and then it just, their head goes crazy. But what you say here, actually, beyond this localization and prioritization, beyond the energy efficiency, you're also working on the functionality of the system. So you're also predicting various failure modes. And even though the pneumatic systems that are considered as the robust system, but still they work for long, we have the problems with the higher friction, with the sealing, with the air quality that also changes, and the downtime of the machine costs sometimes way more than the energy consumption per year. So I think it's incredibly interesting, and especially maybe in one of the workshops in the future, you can teach us about your work because it's really fascinating, and especially about the control strategies. I see now on the market some companies that trying to implement some control strategies into the compressor room. that they're trying to go into the distribution side, and what you do is most on the application side, on the demand. And in my personal opinion, this is my favorite part. So the demand side optimization first. So you're talking about the machine learning, and I see here is like a little bit another angle for this question. Could you please tell us a little bit more about this algorithms of machine learning? How do you use it? Because it's very fancy word, Industry 4.0. Everyone likes it, but now we want to know more. Like the details, the technical details.
Yes. Unfortunately, some do think that if you just apply artificial intelligence, you just get a magic answer. But behind these algorithms, behind the buzzwords, there is also a lot of work which needs to be done, which you would need to teach your systems, to train your systems. So what we are also doing is we're coming up with different control strategies, different control aspects. So how to mitigate the faults without minimizing the productivity. We're trying to model as much of these scenarios as much as we can. And then we would train the algorithms to tell us which combinations would work best. So you might have a situation where you would prioritize, for example, compressed air consumption rather than productivity. So you come up with a pressure reduction, as I said earlier on one line, which would reduce the air consumption, but not the productivity. But imagine the other way around. So you would have a situation where you do have a leak, but productivity time is a really critical issue. So do not come up with options which would reduce my productivity because of a leak that I have on that line. So then the priority would be productivity, but not energy efficiency, not air consumption. So we are coming up with these different scenarios, modeling them, and then use machine learning and artificial intelligence algorithms to try to find the best trade-off between these two sometimes conflicting aspects, because it is very obvious. No, it is not novel, and it is very obvious to tell you that if you have a leak, decrease the pressure. But you would never sell this idea to anyone. So if you tell them you've got a leak and reduce the pressure so that the leak consumes less air, no one would take that on board, because my machinery, my equipment, my assembly, or my pick and place, or whatever it is, I need the rate, I need the output which I require. So trying to find these out of thousands of combinations, we are using now these algorithms to find the optimum, the best combination of productivity and energy efficiency. This is something which I also discuss with my students. Sustainability should not come at the expense of quality or productivity. Sustainability and productivity have to go hand in hand. So selling an option, selling a solution which just improves the energy efficiency, but not the productivity, will never sell. So we would never implement them in industry. So we have to find these trade-offs which do improve energy efficiency, but not at the expense of productivity. And I think this is one of the goals which is motivating us to find the right and optimum solution.
I think it's really great. I always say that the energy efficiency is the result of the system that is designed and that works correctly. So it's the result rather than the goal. So it's hand to hand, as you said. Paul, it's very, very fascinating what you do there. So can you share with us your state of the art now? Is it the lab project now? Because you say you work your research lab that you have students that work on this, and I also know that you have some PhD student, master students. What are the future things? Do you work with industry also? What is your time span?
Good. This research is being carried out in a project which is financed by the Malta Council for Science and Technology. The project is called AirSave, and you can also find the project website, and you can find more details, and more details will also be uploaded in the coming weeks, because we'll have a number of publications which are coming up and you can follow us over there on the website, on Facebook, and on our LinkedIn pages. So you can follow us for more updates over there. So this project, AirSave, is a 3-year project. We kicked off in 2021, following a number of postgrad students which we had before. So this research project, this 3-year project, then follows other work which we did before. In this project now we have 2 PhD students and other master by research students as well. They are using the case studies of our project as their PhD projects, and we are working together with industry. So we have AIM Enterprises, which is a local company here in Malta, which designs and develops pneumatic systems in industry. And we're also working in collaboration with 2 manufacturers here in Malta, Methode Electronics and Tolly Products. They offered their systems for us to use them as our case studies. So what we're doing right now, we generated the data, the metrics, which would be required by the algorithms. So we are in that phase now. We are combining both of them, the data which was generated to be able to model the situations, the scenarios, and now we're modeling them on and classifying them using the AI algorithms. We will be testing them in our lab here at the university. We have a sustainable manufacturing lab, which is quite a brand new lab at the University of Malta. We would be testing them and see how they perform, and eventually take our system to industry. So throughout this project, we envisage that we reach a technology readiness level, TRL level of 7. So we're moving out from our labs, and we are going to test, evaluate the performance of our systems in the intended operational environment. So that would be classified as TRL 7. Obviously, would we be done by the end of this project? So this project would end by the end of this year, 2024. Would we be happy by what we achieved this year? We would, but obviously, this is what happens with projects. Projects generate even more research questions and more objectives, research objectives. And so we look forward to taking that a step further, complicating matters, finding more control situations and scenarios which we would be modeling and training in using algorithms. And obviously we look forward to collaborating with anyone who would be interested to work with our lab here at the University of Malta. Collaboration, we're always open for any collaboration opportunities.
That's great, Paul. I think the last question, one of the last questions I wanted to ask you, I'll play a little bit of a bad policeman here, and like some annoying managers and the companies, and asking you, in terms of the cost of the system. I mean, when the system will be already commercialized, or you find some industrial partners that would like to commercialize, in terms of the sensors, complexity, controls, does it pay back to install it for pneumatic system that are actually sometimes not as expensive as electrical drives?
Okay, another very good question, which hits the nail on the head. And something which I forgot to tell you, what we're also doing is we're carrying out a life cycle assessment. So we are conducting an LCA and a life cycle cost assessment, LCCA. So we want to have a situation where a system, a solution, where it wouldn't just reduce air consumption, but it would reduce air consumption and the energy efficiency behind that air consumption, but in an environmental friendly way. So we are going to compare the carbon footprint and all the environmental indicators behind the system that we are developing. So the sensors, the valves, the controlling elements, against the carbon footprint which would be saved by reducing the energy consumption. So we wouldn't come up with a situation, with a system, which would have a huge carbon footprint and a huge embodied carbon or embodied energy, and save little energy throughout its lifetime, throughout its use phase. And similarly also with cost. So we want to keep costs as low as possible, use minimum sensors as much as possible, possibly even the sensors that we already find in an industrial system without coming up with new sensors and complicating matters. So that it would also be financially attractive. So it would also be financially feasible. We typically know now this might also be on a decrease. Typically, industry has 20-30% of the air lost to leakages. With time, I do know that this percentage might start to decrease with the Green Deal and the Sustainable Development Goals and the Green Agenda. People, industrialists are becoming aware that they would want to improve their efficiency by also reducing the leaks. However, 20-30% might be a lot. As you know, compressed air is widely used. It is very energy intensive, and so we would like to come up with a system which is financially and environmentally feasible to reduce these leaks and improve the efficiency.
Yes, no, that's great. Paul, I'm really happy to see research projects on these aspects, because sometimes people think that it's been forgotten, but it's actually a very hot topic and it's very important. So I really thank you from all my scientific also heart. And I hope for future collaborations, and I hope that we will see more of your research, of your work, and you come also more to our energy movement and podcast, maybe with some workshops, and that you also will find people that would like to collaborate with your lab and your university. Thank you so much for being here today.
Thank you
And
very
good
much.
luck with your project. So we're looking forward to see what's going to be in the end of this year.
Yes, thank you very much. Thank you for your time and for your invitation.
Thank you.